So here's a few examples of finding critical points, classifying critical points, finding maxes and mins, that sort of thing, with functions of two variables. So remember, this is only two variables for these guys. So to find the critical points of a function of two variables, okay, and then classify, remember the first thing to find critical points, I'm going to need the gradient equal to 0. And so if we try that here, find where the gradient 0, or you can think of it where each partial equals 0. So the partial with respect to x, that's going to be 6x squared, just power rule. Y term, that goes to 0, plus 6x, this guy here. Another y term goes to 0. And then minus 12 from this here. And this constant derivative, that guy is also 0. So we got 6x squared plus 6x minus 12. Alright. Solving that for when it's equal to 0, we can actually factor this out. So this is going to be 6 times x squared plus x minus 2, if I factor a 6 out of there, which is 6 times x plus 2 times x minus 1. Alright, so that will equal 0 either when this term is 0, so the x is negative 2, or when this term is 0, when the x is 1. Alright, so that's what I'm going to get for that. Do the same thing with the y. So the partial with y is going to be 0 for the first term, and then 3y squared for the y term. Again, another partial that's 0, and then minus 3, and then the rest is 0. So just 3 squared minus 3. We'll take a 3 out of there, and then this is going to be where y squared minus 1 is 0, so that equals 0 when the y is either plus or minus 1. Alright. So x is negative 2 or 1, y is plus or minus 1. That's going to give us a total of 4 points. So negative 2 for the x, and then either 1 or negative 1 for the y. 1 for the x, and 1 or negative 1 for the y. So you have to mix all combinations of these together. So the more solutions you get to each partial, the more points you're going to have. Alright, so there's our critical points. Now we classify each one. So remember, that's finding the discriminant, and then possibly, if it's not a saddle point, trying to determine if it's a max or a min. So we'll go ahead and do that. So the discriminant, second partial with respect to x, second partial with respect to y, we need to find both of those. So this is going to be second partial. So we have the first partial up here. So that's just going to be a 12x plus 6, then the minus 12 determinant 0. So 12x plus 6. For the y, just going to be a 6y from that first term. The mixed partial, partial with x with respect to y, there are no y's at all, so that partial is just going to be 0, so we can put in a 0 for that. So now we'll go ahead and fill this in for each point. Alright, so for each point I plug in the negative 2 and 1. So the negative 2 for my x is going to give me a negative value. Then the 1 for the y, it gives me a positive 6. Overall, the d is negative. So that gives me a saddle point. Again, plugging in negative 2 and negative 1, we're going to get a negative value here for x. Also a negative value for y. So negative 18 and negative 6, those are going to multiply to a positive. Subtract 0, that's going to be a positive. Okay. If it's positive, you also look at the second derivative of x, which we've already computed. So there's not really anything more to compute. You just have to go back and find it. So that was negative, concave down, so that's a local max. The 1, 1, same thing again. Second partial with respect to x is 18. With respect to y is 6. Mixed partial, 0. Discriminant's positive. We go back and look. The f sub xx is positive. That means a local min. Alright, last one, 1 and negative 1. 18 and negative 6 multiply to a negative. Subtract 0, still negative. So there's a saddle point. So we got 4 points. 2 of them saddle points, and 1 local max, 1 local min. So that's it for those. Alright, so once you find the critical points, okay, classifying, sometimes if there's a bunch of them, it helps to make a table such as this. If there's only 1 or 2, you can just plug in the points right away. Alright, let's try, and here's a little graph of this curve, so you can see some of these points that are in there. So this point right here at, we'll say x is 1, y is 1, That's going to be right there. That's our local min. So you can tell I have a local min right at that point, 1, 1. Over here, where let's say where x is -2 and y is 1, so the x is going to be -2 this direction. The y is going to be 1 around right there. So that's this point right here, so there's a saddle. So you can see it's going up in this direction, parallel to that y-axis, and then down in the x direction, parallel to the x-axis. So there's our points right there on that surface. Let's go ahead and look at another example here. So this one is slightly long just in terms of partials, but same type of idea. Find the critical points and classify as max, min, or saddle. Alright, so if we go ahead and start with this, partial with respect to x and y, we want to solve those for where there's 0. So this one, I'm going to have to do a quotient rule. Alright, so partial with respect to x, derivative of the top times the bottom, minus the top times derivative of the bottom, 2x with respect to x, over denominator squared. So that's negative 9x squared plus 9y squared plus 9 over this denominator. This denominator is never going to be 0, so this is never undefined. So we just need to set that equal to 0, and then we'll get this numerator equals 0. Or dividing by 9, negative x squared plus y squared plus 1 is 0. Alright, so anytime you have a fraction, you'll equal 0 when the numerator is 0, or undefined when the denominator is 0. So it's just going to be setting those two parts equal to 0. If I have a square like I often do with the quotient rule, those are never going to be 0 unless the inside is. In this case, the inside's never 0. So those are usually fairly easy to solve even though they are fractions. I'm just looking at where each piece is 0. Alright, same thing for the partial with respect to y. So partial with respect to y, the top we get a 0, then times the second one, minus the first times derivative of the bottom, which will just be a 2y. So this turns into negative 18xy over that x squared plus y squared plus 1 quantity squared. That will be 0 when negative 18xy is 0 or when xy is 0. Alright, so this is going to give us either x is 0 or y is 0 for that next part. So solve the system of equations. So you don't always get a nice x equals y equals. Sometimes you got to solve. But here, the second equation, I know x is 0 or y is 0. I'll plug that into the top and solve. So if x is 0 from equation 1, I'll get y squared plus 1 is 0. Y squared is negative 1. No critical points. So those are complex. Not going to have any critical points on the graph. If y is 0, equation 1, we plug in the y is 0, and we'll just have the negative x squared plus 1 is 0. So x squared is 1, or x is plus or minus 1. So that came from y is 0. So here we only have two critical points. So those are going to be 1, 0, and negative 1, 0. Alright, so the y was 0, and the x is either positive or negative 1. So those are the two critical points. So once we have the critical points, now we'll go ahead and classify these. So let's see what we got. So d equals f sub xx times f sub yy minus f sub xy squared. And unfortunately, now we have to compute these second partials. So we'll go ahead and try to put these both on a single screen. So here's my first partial with respect to x. It's negative 9x squared plus 9y squared plus 9 divided by x squared plus y squared plus 1 quantity squared. So a second partial with respect to x, that's going to be negative 18x derivative of the top times the bottom minus the top times derivative of the bottom. Derivative of the bottom, I'm going to get 2 times this stuff inside times the derivative of the inside, which is just 2x if I'm with respect to x. So that's all I'm going to get for that guy right there. And then denominator squared on the bottom. So that's a big long function. We'll go ahead and plug in our values. Fortunately, they're ones and zeros, so that makes things go a little bit quicker. But now that I have my partial derivative, now I can go ahead and plug some of these values in. So I'll go ahead and compute them now before I do the partial with respect to y. So if x is 1, this is going to be negative 18, and then 1 and 1, or sorry, 1 and 0. That's going to add up with another 1 to 2. And so I get 2 squared minus this term is going to go to 0. I get negative 9, 0 plus 9 is 0. I don't care what that is if that was 0. Divided by this denominator to the fourth, so 2 to the fourth. Well, 2 squared will divide out with 2 of those down at the bottom. One of the 2's in the 18 will divide out, so I'm just left with the negative 9 halves. So if x is 1, y is 0, that's going to be negative 9 halves. If x is negative 1 and y is 0, it's a similar thing. The only thing that's going to change is going to be this first term. So I get negative 1 times negative 1 is positive 18. All the other terms are the same. So that gives me a positive 9 halves instead. Alright, so there's my two partials with respect to x for each point. Now, just a reminder here was our partial with respect to y. So second partial with respect to y, that's going to be derivative of the top. So with respect to y, that's going to be just the constant negative 18x times the bottom minus the first. So this is negative 18. That should be xy. Fortunately, x is 1 for that one. Times the second one here. So, and the y is 0, so that term's going to be 0 anyway. And then derivative of the bottom, we got 2 times x squared plus y squared plus 1 times the derivative inside, which is the 2x. Alright, denominator is still the same. So this is very similar to the other partial that we found. And here, the f sub y, plug in again. So if x is 1, this is negative 18 times 2 squared. This term is 0 since our y is 0. And I don't care what that is if my y is 0. Down at the bottom, still get 2 to the fourth. So 2 of the 2's divide out, and then another 2 with the 18 gives me the negative 9 halves. The f sub y, can plug in a negative 1 for x. Negative 18 times negative 1 is positive 18. Then multiply by the 2 squared, divide by 2 to the fourth, positive 9 halves. Okay. The f sub xy, partial of x with respect to y. If you want to do that, I can go back and look at the same thing. It's going to be a quotient rule again. So here is our partial of x. Take it with respect to y. So derivative of the top, that's going to be 18y times the bottom minus the top times derivative of the bottom, which is the same thing that we've already seen. So this one, we're going to get the 18y times that bottom minus the top times derivative of the bottom. We've seen those several times. Alright, same thing, denominator raised to the fourth power. The only difference now is, with this guy, I'm going to get 18 times y, which is 0, okay, times, and then that term I don't care. Again, another 0 there, and another 0, so this guy is just going to be 0 again. Alright. So where to go from here? Alright, so that is a big step, finding all those values. Alright, so where we go from there, so for the 0.10, I had partial with respect to x was negative 9 halves, and partial with the second partial with respect to y is also negative 9 halves. Mixed partial 0. So that gives me a positive. Partial with respect to x was negative, so that means local max. So discriminant positive, second partial negative, that means local max at 1, 0. The other one, negative 1, 0, this partial with respect to x, second partial with respect to x was 9 halves, with respect to y was 9 halves, other one was 0, still positive, only this time our second order partials were positive. So here we get a local min. Incidentally, the max and min value are given by the 9 halves if I plug the function in. So if you plug these points back into the original function, you can get 9 halves. It's sort of coincidence that that 9 halves matches with this 9 halves. That doesn't always happen. But those are the values you get there. Alright. And real quick, another picture of this guy. So here's our function there. So at the 0.10, so 1 in the x direction along this x-axis, 0 in the y, so it's right above the axis. That's going to give us that minimum point that's right there. The maximum at 1, 0, so 1 unit in the x direction, so that's right there at 1 unit. And then this will be right above the y-axis because y is 0. So there's that max. Alright, so that's what the graph looks like. You could tell those critical points are maxes and mins from this figure. It's not always quite so easy to tell. Alright, last problem here. Suppose we wish to construct a closed box with volume 32 cubic feet. Three different materials are going to be used in construction, and the materials cost $1 per square foot. Material for the sides. For the bottom, $3 per square foot. For the top, $5 per square foot. What are the dimensions of the least expensive box? Alright, so here's our box. So we have X and Y, and then Z is going to be the top there. And so if we get X and Y, for our sides, we're going to get two sides with area X times Z. Two sides with area YZ. All of those sides are going to be $1 per square foot. Area of the bottom XY, so that's going to be $3 per square foot, and the area of the top another XY, but at $5 a square foot. So let's go ahead and write some of these out. So let's see. So first find the cost function. The cost function, like I said, 5 times that top XY plus 3 times the bottom another XY plus $1 times this side. So we get 2xz's and 2yz's. So simplify that. That's 8xy plus 2xz plus 2yz. So this is a function of 3 variables. Right now we only know how to do a function of 2. But we can get a function of 2 by making a substitution. So the volume we have was 32 cubic feet. So 32 cubic feet, that's going to be the x times y times z. So x times y times z is 32. So we'll get 32 over xy. Substitute that in and see what we get. So the z I'm going to plug in here, and x's divide out. So I just get 2 times 32 is 64 divided by y. I'm going to write that as y to the negative 1. The 32 over xy, plug that in for z, y's divide out. And 2 times 32 again is 64 divided by x. I'll write that divided by x as x to the negative 1. Alright, once we get this, now we can find these minimums again. So hopefully it's a minimum. F sub x, partial with respect to x, that's going to be 8y from here minus 64 times x to the negative 2. So this term 0, and then this last term 64 times the negative gives me minus 64 x to the negative 2. Partial with respect to y, same sort of thing, 8x in this case, and then minus again because I have that negative coming out front, 64y to the negative 2. This last term, derivative 0. So set each of these equal to 0. And so if we set 8y minus 64x to the negative 2 equal to 0, that means the 8y has to equal 64x to the negative 2, or dividing by 8, y is 8x to the negative 2. Same thing on the bottom. Solve for x. We're going to get x is 8 times y to the negative 2. Alright, that's a system I need to solve. So we can solve that just by a regular substitution. So we'll substitute y into our equation right here. So substituting y, we'll get y as 8x to the negative 2. Sorry, substituting x. So x is 8y to the negative 2. That goes into our top equation for x. Alright, so we get y is 8 times 8y to the negative 2. That used to be the x. Again to the negative 2. So we got y is 8 times 8 to the negative 2. And then this negative 2 times negative 2 gives me positive 4 for that power of y. So I'm just multiplying those exponents. 8 times 8 to the negative 2, I'll add those exponents. So that gives me 8 to the negative 1. And then divide both sides by y. That gives me y cubed. So I got 1 is 8 to the negative 1 y cubed. So this 8 equals y cubed. I can get that from 1 equals 8 to the negative 1. So if I divide 1 divided by 8 to the negative 1, that 8 now becomes 8 to the positive 1. So we get y cubed equals 8. So anytime you divide by a negative exponent, remember you can put that in the numerator, make that a positive exponent right there. Alright, once I get to this 8 is y cubed, take the cube root, so we get y is 2. Alright, so lots of exponential rules in through there. Alright, well there's our y. Now I just back substitute to get x. So the y is 2, so I can plug that in here. So we get x is 8 times 2 to the negative 2, which is a fourth. 8 over 4, x is also 2. So there's the y is 2, the x is 2. To get z, z is going to be 32 over 2 times 2, which is 8. And depending on how the problem goes, we have dimensions. X is 2, Y is 2, Z is 8. You may need to justify that's a min. If I say don't justify that's a min, then you can leave it right there. We'll go ahead and justify for this one. So to justify doesn't take too long. Second partial's test again. So the second partial's here. Second partial with respect to x, so that's 128x to the negative 3. Second partial with respect to y, that's going to be 128 times y to the negative 3. And then the mixed partial, so partial of x and then y, that's just going to be the 8 from this 8y term right there. So we'll go ahead and justify this. So the discriminant is going to be the second partial at 2, 2. So that's 128 to the negative 3. Turns out to be 16. Second partial with y, it's the exact same thing. Also 16. And then minus 8 squared. So 16 times 16 minus 8 squared, that's a positive number. Derivative is positive. Second partial with respect to x, also positive. So that is a minimum. So it does minimize cost. Like I said, unless it says to do this step, like for instance on a test, just to save time, where I may say, you don't have to justify, just find the min, if it's a word problem such as this. So here the dimensions that we're going to get are going to be x is 2, y is 2 for those two bottom sides, and then the height is going to be 8.